Hello, everyone, and welcome to episode 0 of the SES Network course. I'm Alex Liu, DevRel at SES, and I've designed this episode specifically for students who may not have prior experience with blockchain and Web3. Since SES is a blockchain powered network, it's essential to first understand how blockchain works before we dive into the SES Network course. By the end of this lesson, you will have a clear understanding of what the blockchain is and how it works, why decentralization matters, how smart contracts and dApps function, and most importantly, how SES storage can be integrated into applications. If you're already familiar with the blockchain, you're welcome to skip this episode. However, keep in mind that you must still complete your exercises, as your score contributes to your final ranking in this course. Now, before we begin, a quick note. For the rest of this course, Hari Casado will be leading the lessons, and I'll be guiding you only through this special introductory episode. So if you notice a change in voice or teaching style in later episodes, that is why. Alright, let's get started. Now that we're all set, let's take a look at how this course is structured. This course is divided into 11 episodes, covering everything from basic concepts to advanced development. Each episode will be released on weekly basis, ensuring that you have enough time to learn, practice, and complete the assessments before moving forward. Here's what you can expect. Today's episode, episode 0, is an optional yet highly recommended introduction to blockchain for those who are new to Web3. Episode 1 to 3 will cover the SES network architecture and how it operates, the key technologies that make SES unique, and the ecosystem and real world applications of SES. Episodes 4 to 6 will be hands on, focusing on running nodes on the SES network, setting up accounts, and participating as a miner. Episodes 7 to 10 will take us into development, covering building dApps using Ink and Solidity smart contracts, developing custom palettes to extend the SES blockchain. At the end of each episode, there'll be an exercise to test your understanding. These exercises are not just for your practice. Your scores will be contributed to your final ranking in the course, so participation is important. A few important things to note here. Firstly, the new episodes will be released every week. Secondly, keep an eye on the SES course website at course.ses.network for schedules, updates, and additional resources. Lastly, if you have any questions, connect with us on Discord. The link is available on the course website. Our team and community members will be happy to help. Alright, now that you know how the course is structured, let's get started with our first topic. What is blockchain? To understand blockchain, let's first look at how traditional ledgers work. In our everyday world, financial transactions are recorded in a centralized ledger maintained by a trusted authority, like a bank. Whenever you deposit or withdraw money, the bank updates its ledger to reflect the new balance. The problem over here is, since the ledger is controlled by a single entity, you have to trust the bank won't make mistakes, manipulate records, or restrict access to your funds. There's also the risk of hacks, fraud, or system failure that could compromise your money. Now, imagine a system where no single entity controls the ledger, and instead it is maintained by multiple participants across the world. This is where blockchain comes in. A blockchain is a distributed digital ledger that records transactions in a secure, transparent, and tamper proof manner. Unlike traditional centralized databases, blockchain operates on a decentralized peer to peer network, meaning no single authority owns or controls the data. Instead of a bank or company maintaining the ledger, blockchain distributes it across thousands of computers worldwide. This prevents a single point of failure and enhances security. Once the transaction is recorded, it cannot be changed or deleted, meaning that it is immutable. This ensures data integrity and prevents fraud or manipulation. Also, every transaction in a distributed ledger is publicly recorded and verifiable by anyone on the network. While personal identities remain private, the transaction history is open to all, making it transparent, which creates trust in the system. Lastly, blockchain uses cryptographic hashing to secure transactions. Each block contains a unique cryptographic hash that links it to the previous block, making it nearly impossible to alter past data, making the network highly secure. A good way to think of blockchain is like a shared Google document, but instead of one company controlling it, Everyone on the network has a copy, and once something is written, it cannot be erased or changed. Let's take a look at the diagram below to understand this better. So here we can see we have our first block. The block can contain many things like transactions, noise in case of proof of work consensus mechanism, metadata, and so on. The first block is known as the Genesis block. It has a unique hash but no previous hash, which is represented as 0000. So hashing is a technique used by blockchains which uses Merkle trees as a way to encode blockchain data more efficiently and securely by hashing transactions and resulting hashes into a hash called Merkle root. The Merkle root is used to create the block hash, a block's unique identifier. When a new block is created, it contains a unique hash derived from its data, the previous block's hash, creating a chain-like structure. Now, if anyone tries to alter a previous block, even by changing a single digit, the hash of the block will change completely. This will break the link to the next block, making it obvious that the data has been tampered with. This is why blockchains are so secure. If a hacker wanted to alter a transaction, they would have to change every subsequent block. Now that we understand what blockchain is, let's take a look at how it actually works when a transaction is made. We'll go through the entire process step by step to see how transaction moves through the blockchain network and gets permanently recorded. In the first step, transaction is created and broadcasted. Imagine that Alice wants to send 1 Bitcoin or CES token to Bob. To do this, she creates a transaction which includes the amount being sent, 1 BTC or 1 CES token, the sender or the receiver's public addresses, a digital signature which serves as Alice's proof that she authorizes the transaction. Once the transaction is created, it doesn't get confirmed immediately. Instead, it is broadcasted to the network. Similar to how emails is sent to multiple recipients, every node in the network receives a copy of the transaction and waits for it to be processed. In the next step, the transaction is added to the block. Now that Alice's transaction is in the network, it first joins a pool of pending transactions where it waits to be processed. At regular intervals, a group of transactions is collected into a block, which will soon be validated by the network. Think of this like a page in a ledger. Before it is permanently recorded, it needs to be reviewed and approved. In the next step, the block is sent to every node in the network. Once the block is created, it doesn't just stay on one computer. Instead, it is distributed to all the nodes in the network. Each node receives a copy and gets ready to verify the block's transaction. In the next step, node validates the transaction using consensus. Before a block can be added to the blockchain, it must be verified by nodes. But how do nodes agree on whether a transaction is valid or not? This is where consensus mechanisms comes into play. Different blockchains use different rules to achieve consensus. For example, proof of work used by Bitcoin, where miners solve complex mathematical puzzles to validate transactions. Proof of stake used in newer blockchains, where validators lock up their cryptocurrency as collateral and are selected to verify transactions based on their stake. Once the majority of nodes agree that the transactions in the block are valid, the block is confirmed and marked as final. In the next step, nodes receive rewards for verification. To incentivize network security and participation, nodes that validate transactions receive rewards. This could be in the form of transaction fees paid by the users or newly minted cryptocurrencies issued by the blockchain. For example, in Bitcoin, miners receive a block reward plus transaction fees when they successfully validate a block. The system encourages more participants to secure the network, keeping it decentralized. Next, the blockchain is added to the existing blockchain. Now that the block has been verified, it is officially linked to the previous block in the blockchain. This ensures an unbroken chain of transaction history, where each block is connected to the previous one through cryptographic hashing. If someone were to attempt to alter a past transaction, they would have to change every block after it, making tampering nearly impossible. Finally, the transaction is complete. At this point, Bob successfully receives 1 BTC or 1 CES token from Alice. The transaction is now permanently recorded on the blockchain and cannot be changed or removed. This entire process from transaction creation to final confirmation typically happens in a matter of minutes in a blockchain like Bitcoin, or even faster on more scalable networks within few seconds. Now that we understand how blockchain works, let's take a look at two main types of blockchains, public and private. Both serve different purposes, and depending on the use case, one might be more suitable than others. Let's start with public blockchains. These are completely open networks where anyone can join, participate, and validate transactions. Public blockchains are designed to be decentralized, meaning no single authority controls them. Instead, thousands of independent nodes work together to verify transactions and secure the network. To ensure trust and security, public blockchains rely on consensus mechanisms like proof of work (POW) or proof of stake (POS). This allows anyone from anywhere to contribute the network without needing permission. Since there's no central authority, public blockchains are highly resistant to censorship. No one can alter or delete data once it's recorded. A few well known examples of public blockchains include Bitcoin, which is the first most widely known cryptocurrency, Ethereum, which introduced smart contracts and decentralized applications, and CES, which is designed for decentralized data storage. However, because public blockchains are open to everyone, they tend to be slower and more expensive than private blockchains. Every transaction must be verified by many nodes, which increases security but also adds processing time and costs. Now, let's talk about private blockchains. Unlike private blockchains, these are restricted networks where only authorized participants can join and validate transactions. Private blockchains are commonly used by enterprises and organizations that require controlled access and higher scalability. For example, a financial institution may use a private blockchain to securely manage internal transactions without making them publicly accessible. These blockchains are usually centralized or semi centralized, meaning a single entity or a consortium of companies have control over the network. Because private blockchains have fewer participants, transactions are processed much faster compared to public blockchains. They also allow businesses to customize their blockchain rules and privacy settings according to their needs. Some well known examples of private blockchains include Hyperledger Fabric, which is used for enterprise solutions, and R3 Corda, which focuses on financial applications. While private blockchains offer high speed and scalability, they lack decentralization of public blockchains, meaning the data and control remain with a limited group of entities. So, in summary, public blockchains are more decentralized, open, and trustless, but can be slower, whereas private blockchains are faster, more controlled, and better suited for enterprise use case. Now that we understand the difference between public and private blockchains, let's break down the key components that makes up the blockchain and how they work together. At its core, a blockchain consists of four key components: nodes, consensus mechanisms, smart contracts, and transactions. These elements work together to ensure security, decentralization, and reliability of the network. Let's start with nodes. Nodes are computers that store and validate blockchain data. They maintain a copy of blockchain ledger and continuously update it as new transactions occur. Nodes ensure that entire network remains synchronized, meaning that everyone in the system agrees on some version of the ledger. Without nodes, blockchain wouldn't function, as they are responsible for verifying and relaying transactions across the network. Now, how do these nodes agree on which transactions are valid? That's where consensus mechanisms comes in. Since blockchains are decentralized, there is no single authority to verify transactions. Instead, blockchains use consensus algorithms to achieve agreement amongst participants. The two most common consensus mechanisms are proof of work (POW) used in Bitcoin requires miners to solve complex mathematical puzzles to validate transactions. While highly secure, it consumes a lot of energy. On the other hand, proof of stake, used by many modern blockchains, selects validators based on the amount of cryptocurrencies they stake in the network. It is more energy efficient than proof of work and allows faster transaction processing. Next, we have smart contracts. Smart contracts are self executing agreements that run on the blockchain. Unlike traditional contracts, which requires a middleman like a bank or lawyer, smart contracts automatically executes when predefined conditions are met. For example, in a decentralized crowdfunding platform, a smart contract could automatically release funds to a project once a funding goal is reached. Finally, we have transactions. the core activity in any blockchain. Transactions represents the exchange of data or value on the blockchain. Whether it's sending cryptocurrency, executing a smart contract, or storing data, every operations on the blockchain is recorded as a transaction. Once validated, a transaction is permanently added to the blockchain ledger, ensuring transparency and security. To summarize, nodes maintain and verify the blockchain. Consensus mechanisms ensure agreement on transactions. Smart contracts enable trustless automation. Transactions are the fundamental operations recorded on the blockchain. Now that we have covered the fundamentals of blockchain, let's take a step back and look at how the internet has evolved over time. This will help us understand why decentralization is such a big deal and why Web3 is shaping the future. The internet has gone through three major phases: Web 1.0, Web 2.0, and Web 3.0. Web 1.0 is the early internet, which is read only era. Web 1.0, which exists from the 1990s to early 2000s, was static and read only. Websites were simple, with basic text and images, and users could only consume content without any real interaction. Think of Yahoo, MSN, and early blogs. They provided information, but you couldn't post comments, share content, or create accounts. Web 2.0, it was the interactive era, which allowed read and writes. Web 2.0 introduced user generated content and interactivity, allowing people to post, share, and engage with online platforms. Social media, e commerce, and cloud services flourishing during these periods, giving rise to platforms like Facebook, YouTube, Instagram, and many more. However, there's a major problem with Web 2.0, that is centralization. A few corporations like Google, Meta, or Facebook and Amazon control the internet. Users' data is stored in centralized servers, making it vulnerable to hacks, censorship, and misuse. Platforms profit users' data while users have no control over their own information. This is where Web3 comes in. Web3 is the future of the internet, which is the era of read, write, and own your data. It is built on blockchain technology and is all about decentralization, data sovereignty, and user control. The key benefits of Web3 includes data sovereignty, where users own and control their data rather than the corporations. It is also censorship resistant, where no central authority can block or restrict access to information. Tokenization and decentralized finance (DeFi) allows users to participate in open financial systems without intermediaries. Decentralized networks, platforms like CES allows users to store and retrieve data without relying on centralized servers. To put it simply, Web 2 gives us interactivity, but at the cost of control. Web 3 is about taking back ownership and putting users in charge. Now that we understand the shift from Web 2 to Web 3, let's talk about one of the key technologies that powers decentralized applications, that is smart contracts. A smart contract is a self executing program stored on a blockchain that runs when specific conditions are met. It automates agreements between two parties without needing a middleman. To better understand this, let's compare traditional contracts and smart contracts. Let's say two people agree on a deal. They sign a contract, but they need a third party, a bank, a lawyer, or a notary, to enforce it. Finally, the contract is executed. This adds costs, delays, and trust issues because you must rely on the middleman to ensure both sides follow the agreement. On the other hand, with smart contracts, the process is fully automated. The agreement is written as code and stored on the blockchain. Once the conditions are met, the contract executes automatically. No lawyers, no bankers, no delays. The transactions are transparent, immutable, and trustless. Let's take a look at some real world examples. Decentralized Autonomous Organizations, or DAOs. These are the groups that runs on smart contracts instead of human management. Example: MakerDAO. NFT marketplaces. Platforms like OpenSea uses smart contracts to handle ownership transfers of digital assets. Decentralized finance, or DeFi. Platforms like Uniswap or AAVE uses smart contracts to automate lending, borrowing, and trading without banks. Think of smart contracts like vending machines. If you put in the correct amount of money and press a button, you get back snacks. No human intervention needed. Blockchains ensures that the contract executes fairly every time. Now that we have understand smart contracts, let's compare the two major blockchains ecosystem that supports them. Ethereum and substrate-based blockchains like SES. Ethereum is the most well-known smart contract platform, but substrate-based blockchains like SES offers more flexibility and efficiency for certain applications. EVM-based smart contracts uses Ethereum virtual machines to process smart contracts. Solidity is the primary programming language for writing contracts. It has vast ecosystem but faces scalability issues and high gas fees Due to network congestion. Ethereum's model is general purpose, meaning it's great for many applications but not highly customizable for specific blockchain needs. Substrate blockchain based smart contracts uses WebAssembly, which is more efficient and flexible than Ethereum or EVM. Smart contracts on Substrate uses Ink, a Rust based framework optimized for security and performance, and it is also customizable. Developers can fine tune blockchain logics, consensus, and features to match their project's need. Interoperability: Substrate chain can interact seamlessly with Polkadot's ecosystem. So, in simple terms, Ethereum is great for general purpose dApps but struggles with congestion and high fees. On the other hand, substrate based chains like SES provides more control, customization, and efficiency, especially for decentralized storage, AI, and data applications. Finally, now that we have explored smart contracts and their different environments, let's talk about what they enable, that is, decentralized applications or dApps. A DApp or a decentralized application is an application that runs on blockchain instead of centralized servers. Unlike traditional apps, DApps are trustless, transparent, and resistant to censorship because they operate using smart contracts instead of relying on a company's backend servers. So, how are DApps different from traditional apps? Traditional apps like Facebook, Uber, or Amazon run on centralized infrastructures controlled by a single company. This means users' data is stored on private servers, making it vulnerable to data breaches or censorship. The company can change policies, ban users, or restrict content at any time. Transactions go through intermediaries, adding fees and delays. However, with dApps, they run on blockchains, meaning data is decentralized and controlled by the network instead of a single entity. Smart contracts ensures the transactions and logics execute automatically without middleman. Users have the full control over their data and digital assets. Some of the real world examples of dApps are DeFi, decentralized finance, which we saw earlier, platforms like Uniswap, AAV, NFT marketplaces, again, and gaming and metaverse. Games like Xe, Infinity, and Decentraland uses blockchain to enable true digital ownership of in-games assets. So in short, dApps are applications that remove middlemen and gives users direct control over their transactions, data and assets. Congratulations, this is the end of this episode. Now that we have covered the fundamentals of blockchain, Web3, we are ready to dive into SES network and its role in decentralized data value infrastructure.